Hello, everyone. Welcome to Astronomy on Tap number 106, and also Happy Earth Day. It's a very appropriate occasion for Astronomy on Tap. We picked some topics that are marginally more related to the Earth than some of our last ones have been. You'll hear more about the Earth and telescopes on Earth and the Moon, which is around the Earth, than stars. So it's sort of an Earth theme for Earth Day. Our next Astronomy on Tap is right here on May 20th at 7 p.m. Astronomy on Tap is the third Wednesday of the month. It used to be penultimate Wednesday, and people said that was confusing. So now it's the third Wednesday, because that's easier. So today we'll be hearing from Hurum, Maksora, Tohfa about the art of seeing inside Rubin's optics. And then, after an intermission, we'll hear from Professor James Davenport on Apollo 14, very mysteriously titled. I'm sure you can't guess what it's about. But first, some trivia. The trivia will have 10 questions. There will be 4 multiple choice answers for each one. And the first 5 will be relating to one of the talks, and the second 5 will be relating to the second talk. Hopefully, by the end of the talks, you will have figured out if you got some of the questions right or wrong. And if you do the best of anyone, you'll get some prizes. And also probably if you're second or third best. So, without further ado, let us begin. I'm going to run through these questions once, and I'm going to read them out loud, and then I'm going to run through them again faster afterwards, and I'm not going to read them. You only get one chance to hear me read the questions. Question 1. What is the primary optical design used by the VRC Rubin Observatory Telescope? Is it A, a 3-mirror anastigmat, B, a Ritchie-Chrétien telescope, C, a Schmidt camera, or D, a Gregorian telescope? Am I too loud? Question 2. The effective focal ratio of the Rubin Observatory system, is it the closest to A, f over 8, B, f over 1.2, C, f over 4, or D, f over 10? Now this is of course a fairly jargony question for camera and optics stuff, but hopefully you will learn some things after our first talk and we'll be able to think more about it. Question 3. Which component accounts for field curvature and aberrations in the Rubin optical system? Is it A, the secondary mirror, B, the tertiary mirror, C, the primary mirror, or D, the refractive corrector? One of these things is not like the other. Question 4. What is unusual about the primary and tertiary mirrors in Rubin's telescope? Is it A, they are segmented like the Keck telescope? Is it B, they are made of silicon carbide? C, they are separate mirrors mounted independently? Or D, they are monolithic, which means they share the same substrate. They're made out of the same exact material. Oh, no. Question 5. The Rubin Observatory's high image quality and accurate focusing are primarily enabled by, is it A, the adaptive optics system, B, its large refractive corrector assembly, C, an extremely long focal length, or D, interferometric Interferometric. Interferometric baseline combination. In editing this question, I rearranged the order, so we'll have to fix that later. All right, those were the Rubin questions. Now, onto some Apollo questions. Question 6. Which astronaut on Apollo 14 famously hit golf balls on the lunar surface? Was it A, Edgar Mitchell, B, Alan Shepard, C, Stuart Roosa, or D, John Young? Question 7. Apollo 14 landed in which lunar region? Was it A, Mare Tranquillitatis, or the Sea of Tranquility, B, Oceanus Procellarum, C, Mare Imbrium, or D, the Fremaro Formation? Question 8. What was the primary scientific goal of Apollo 14 as compared to Apollo 13? Was it A, to test lunar rover mobility, B, to demonstrate an orbital rendezvous, C, to complete a geological survey, or D, to deploy a space telescope? Question 9. Which experiment deployed by Apollo 14 measured subsurface structure and the elastic properties of the moon? Is it A, the laser ranging retroflector, B, the solar wind composition experiment, C, the charged particle lunar environment experiment, or D, the active seismic experiment? And question 10. What unusual payload did Stuart Roosa carry into lunar orbit? Is it A, a prototype spectrometer, B, a biological experiment with mice, C, meteorite samples, or D, tree seeds? Give you 15 seconds per question. Next to 1. And that brings us to the end of our trivia segment. While we switch over our computers so that you'll be able to see the slides for the next talk, if you would please come up and turn in your slips so that we can grade them, and then we'll let you know who won. All right, thank you all for bearing with us while we got through some minor technical difficulties. Today, our first talk will be The Art of Seeing Inside Rubin's Optics. This talk will be given by a third-year graduate student in the University of Washington Astronomy Department, Hurum Maksora Tohfa. Give it up.
Hi, thanks everyone for coming. So today we're going to talk about Rubin's optics. So when you're building a huge telescope like Rubin is, you have to think about a lot of things. Since it's the biggest survey telescope ever to exist, you have to pick a very nice location. So what does a really nice location mean for a telescope, right? So you want to be somewhere where there's not a lot of interference. For example, if we build the telescope in Seattle, half of the year it rains. So we can't really see anything half of the year. But then also, if it's too humid, then you have this issue, then you have a lot of interference in the atmosphere that you have to go through to see your targets. So it just happens to be the case that one of the best places for building a telescope is a mountain called Cerro Pachon in Chile. And so Rubin telescope sits up there about 3,000 meters up. And it's a wonderful place for having a big survey telescope such as Rubin. So a lot of you have heard a lot of talks on Astro on Tap about Rubin, but just to reiterate why we built this huge survey telescope, the big science goals we want to answer are, since this is going to be a 10-year-long survey and we're mapping the whole southern sky, we can try to trace how dark matter is distributed, or see by observing the galaxies if we can tell more about dark energy. We can see, since it takes a picture of the sky every 30 seconds, we can also do things like when we see flares of like an object that's exploding, such as supernovae, we can constantly take pictures and understand more about such objects. Since Rubin has outstanding depth, we can also see a lot of objects in our own solar system that has never been seen before. So Rubin is supposed to discover 5 million asteroids and other objects in our solar system that we haven't seen yet. And it's also going to map our whole galaxy. So to give you a sense of how big of a scale we are mapping with Rubin, so think of a full moon when you look at the sky. So imagine 40 of those full moon. That's how much we're looking at through every single exposure with Rubin. And then we take a picture like that every 30 seconds, and we do it for 10 whole years. And as you can see, each picture has 3.2 billion pixels. So just imagine, compare that with whatever camera that you are used to. That's the kind of resolution that we're talking about. So we're very excited about this. But then the question becomes, how does a big telescope like this work? How do we get that kind of resolution? So the telescope is kind of like, it's done with these like 3 mirrors. So the first mirror, or M1, you have this huge amount of light that's all pouring in to the first mirror. And then because of the curvature of M1, that light gets reflected back, and it gets narrowed down so that it can converge. Then we have M2, which is another mirror that is curved differently than M1, which reflects the light back. Again, it's again trying to converge the light. And then finally, M3, which is a part of M1 and M3, are basically one single mirror, but that has 2 different kind of curvatures. So basically, we take all these photons and we bounce them back and forth to converge them to a very small amount of surface so that we can get a very clear picture. So this is what I was talking about. Basically, the M1, M3 is like one mirror plane, but you have two different kind of curvatures. And it's important to note that under these mirrors, also behind M2, there are a lot of these pistons that you can move around to do different kind of things. This is going to be relevant in a little bit. So now we talked about this big telescope, and you have all these mirrors that are in place. However, even though ideally we would like it if it just like stayed still, it doesn't. It's hard to keep a telescope that big just still and stationary to take all these perfect science images that we want to take. The main issues that we kind of see are with gravity, wind, temperature. So when we say gravity, your telescope is tilted at some angle, and different part of the telescope is experiencing slightly different amount of pull. And because for this we need very, very precise images. It's very important that we correct for every minor changes. Again, temperature. The temperature on the outside of the surface is going to change a lot quicker than the inside. So you have to constantly keep making these adjustments. When the wind is gushing in, some part is getting moved in a certain way. So all these minor things have to be constantly corrected so that we can maintain the kind of quality for the great science goals that we have. So when we talk about having a good image, what we mean is something we call seeing. So it's determined by something we astronomers call arc seconds. It's a unit which is, if you are looking at the width of a penny from 2.5 miles away, that's the angle that we're talking about. That would be an arc second. So the error budget that we're looking at with Rubin is the atmosphere itself is contributing about 0.65. That's median seeing contribution just in our location. And we have to do better than the atmosphere so that we don't run up the error budget too much. And we're going to get to this in a second. Active optics is the constant adjusting thing that I was talking about. So we have to do that. So what does it mean when I keep saying it has to be perfect? What are these adjustments? So basically, if you have lights coming in, if they don't come to a single point, the picture just looks blurry. So what you ideally want is all of your light converging to like a nice single point. Then you have a very sharp image, which has wonderful seeing, right? So what active optics try to do is it's trying to measure how much of this thing is happening. So we can go from here to here. So then the next question becomes how we do that. So every kind of distortion that we see, it can be decomposed with some spherical functions. And the details isn't very important. The primary things that we care about are how much it's getting defocused, how much astigmatism there is. It's similar to people who have eye condition. And then there are secondary terms which also show these similar effects. So then what's the solution? So we get Rubin to kind of look at what it's seeing, and we try to teach it how to adjust itself. So we do it in two steps. One is something, so we call the first part the open loop and the second part the closed loop. So the open loop is a simple lookup table where we have a simple equation. We can look at whatever temperature for the day is. We can think about which angle we want to align our telescope at. and we can make some adjustments to make sure that our telescope is focused. However, it always turns out that there are also some secondary corrections that are always needed. So we basically try to correct for those secondary terms using the small order corrections that I was talking about in the last slide. Once we have those, if you remember in the beginning, I was talking about the 156 pistons behind the M1, M3 mirror. So these pistons can be moved to the telescope. The mirror itself, it's not a still stationary object. It's more like something made of steel and glass, and there are ways to bend it, so you can move those pistons to make adjustments to all three of those mirrors. So there are basically 50 knobs you can essentially tune to focus your telescope. So how do we do this, right? So to do this, we take out of focus images. When you take out of focus images, instead of looking like a point, if you remember from the first pictures, you have the secondary mirror blocking the light, and you have the primary mirror. So when you take an out of focus image, they kind of look like donuts. And we use these donuts if we are perfectly in alignment. That would mean that our telescope is focused. However, if we're not completely focused, we can see that the donut kind of starts to look oval shaped, or if it's kind of lopsided, then we say something called coma. But usually you wouldn't see just one effect. It's usually a combination of a bunch of effects that we look at. So here's one of our example cases where we tend to take one intrafocal out of focus image and extrafocal out of image, just so that we can tell which way we need to make the adjustments. Otherwise, we wouldn't know the sign of the correction that we need to make. So once you kind of like see, by the time we keep constantly making these adjustments, we find these perfect round donut shapes. That means our telescope is perfectly on focus. And when that happens, we love that. You might be wondering then, okay, we just turn on a telescope and it just does its thing. No one has to do anything. That's not how it works. So the whole night, it takes a bunch of image. It's constantly adjusting itself, trying to do its thing. At the bottom of the primary mirror, we also have a laser tracker that shoots up the beam at the beginning of every night and makes sure that the things are where they're supposed to be during the day. We do a lot of engineering things. So it's very important that we first align everything almost properly, because the both the lookup table and the open loop can make some corrections, but it can't go from a telescope being completely misaligned to perfectly in focus. So it does need a little bit of help, and that's where we use our laser tracker every night, and then we do all the open loop, closed loop cool things. Now, once we do all of our corrections, if you remember, I was just talking about all the 50 little knobs that you can tune, but even that's a lot of things to do. And sometimes it turns out a few combination of them can produce the same effects. So we basically take that and we turn them into this basis function where we only turn those knobs which can show clear effects and push down everything else that's under our noise that's under noise level, and we don't make any adjustments to them. So that's the actual correction that we make. We measure the corrections with our active optics, which is the open loop donuts. Once we have those corrections, we turn them into some kind of mathematical formula, and then we turn the knobs. All this exciting stuff came to a fruitful result when we saw our first image about a year ago today on April 15th. We saw Rubin's first image. As you can see, it can focus wonderfully. You see all these beautiful galaxies and stars and everything, so which is awesome. So this talk is also very special today because it's about our first year anniversary since our first light. So something really great about this kind of work is that whenever you make these kind of adjustments, you come up with these new methods for running such big telescopes. The next generation of telescopes can use things like this. Some of our ideas were taken from other previous telescopes. So the upcoming telescopes, GMT, TMT, those kind of things would be using the Rubin's active optics that we came up with, and this is going to have a very long-term effect, and we're also very excited for its 10-year survey. So if there is just one takeaway you want to take from how we run Rubin, it's we taught a telescope to look at itself and make the adjustment that's necessary. So it's kind of like this great self-contained thing that can give excellent performance at focusing itself. While we're almost at the end of the talk, I wanted to say Astronomy on Tap is really great because we get to share all the great science that we do. We also try our best to do other outreach events. The students from University of Washington, we also go teach at a youth prison where we try to teach incarcerated young kids. So if you are in any way affiliated with the University of Washington and interested in volunteering, please let us know. We would always love new volunteers. But if you can't do that, but interested in contributing in either way, you can scan this QR code. And in the description, if you write eSTEAM, we can use this money to help kids. We run different programs. Like last summer, we ran a robotics camp. This is us preparing for the robotics camp. We took solar telescope at a prison, and the kids drew what they saw. It's a wonderful experience. So if you want to contribute in any way, that's always appreciated. I'll put this slide up during intermission. And thank you so much. Any questions?
You could repeat the question into the mic.
Yes.
How much works is that going to have an effect over like 10 years?
It's not big enough that it's gonna completely bend the telescope because these adjustments are very smooth because our air budget is very small. So yeah, those things there has been a lot of engineering decisions that went into making this. Thank you. Yes.
When do you see the primary scientific mission of Rubin start?
When do I see the
Like the full-scale data gap.
So we are starting commissioning any day now, but there are some small issues. But already we have seen a lot of new asteroids. So currently, in the position that Rubin is, although we're not entirely in the commissioning mode, we're still discovering new objects, and yeah. So maybe within the next few months, we're gonna go into the 10-year survey mode. Yeah. Yes. So that's a very good question, right? So we want to image the sky every 30 seconds. So this adjustment has to happen from first image to the second image. But right now it takes 2 more images. So you're looking at one image by, not the next image, by the next one. This adjustment has already been applied. Yes.
When you're adjusting the image, what's the baseline you use, and how could it be? Is there a potential that you're missing events, like like a gravitational lens that you're interpreting as misfocus?
Well, we're taking images every 30 seconds, so it's like going this, this, this. So a gravitational wave wouldn't be, yeah. And also we don't, this is a survey telescope with just like imaging the sky. That's not the same as LIGO, for example, who are detecting gravitational waves. If
But
that,
what's your, in those image, what's the baseline that you're measuring that makes you think you have a correct image?
oh, how do we know if we're getting the correct image? So if we're out of focus, then we already know. Yeah, if you're not exactly in focus, your images would just look like smear. Your star would be like this big. So we can calculate something called the point spread function for every object that we see. And if it's too big, then we already know that it's not in focus. Yes. Sorry? We take images in like 6 different bands, and then using those, we can make the colors. I believe Rubin data is public. What we do with the data is we do a lot of exciting science that I talked about in the beginning. Oh, it's in the clouds. Yes. Sorry? So you can kind of see the satellite trails because they're changing from each image to image. So it's not really, am I understanding? Yeah, you can tell. Yeah. I don't work on that, so I don't know. Sorry. Yes. No. All right. That's yes. Last one. I don't know. Do you know how many supernovas we're expecting to see? You're the supernova person, kinda. Sorry, we don't know. Thank you.
So now it is time to quickly go over the trivia answers, and then we'll have a brief intermission, and then our next speaker. So the answers to these trivia questions. Question 1. This question asks, what was the primary optical design used by the DiRAC Rubin Observatory Telescope? This is a 3-mirror anastigmat. This is what Hurum was talking about, where you have the tertiary mirror up top, and then you have the 2 mirrors that are both connected, but they are at different angles. So it's 3 mirrors, but 2 of them are connected. Question 2, the effective focal ratio of the Rubin Observatory system is closest to f over 1.2. I don't have anything more to say about this. I don't even know what that means. Question 3, which component accounts for field curvature and aberrations in the Rubin optical system? This is the refractive corrector. This is the system that corrects for refraction. Makes sense. Question 4. What is unusual about the primary and tertiary mirrors in Rubin's telescope? This is they are monolithic and share the same substrate. So they're made out of the same material, and they are physically connected inside of the telescope. You have the secondary mirror up top, and then the primary out on the edges, and the tertiary in the middle. Question 5. The Rubin Observatory's high image quality and accurate focusing are primarily enabled by the adaptive optic system, which is also called the active optic system, depending on who you ask, which was what Hurum's talk was all about. Question 6. Which astronaut on Apollo 14 famously hit golf balls on the lunar surface? This was the captain of the mission, Alan Shepard. He thought it would be funny and wanted to see how a golf ball flew on the moon. Question 7. Apollo 14 landed on which lunar region? This was the Fra Mauro formation. They were completing a mission that Apollo 13 was supposed to do, but they had to abort their mission. What was the primary scientific goal of Apollo 14 compared to Apollo 13? This was to complete the geological survey that Apollo 13 was supposed to do, but that Apollo 14 had to take over instead. Question 9. Which experiments deployed during Apollo 14 measured subsurface structure and elastic properties of the moon? This is the active seismic experiment. And they also brought a passive seismic experiment that just sits there. The active seismic experiment, it is active. They were not kidding. It throws grenades at the ground to test how the explosions affect the lunar surface. It is active. And question 10. What unusual payload did Stuart Roosa carry into lunar orbit? This is D, tree seeds. These then became moon trees as part of an experiment that discovered that they actually grew still pretty well. So those are the trivia answers. There is one team that got 9 points, and this is Team Sarah is the Best. Now, I think this may be the wife of our next speaker, so I don't know if that counts, but good work anyway. But then, there is actually a 5-way tie for actual first place, and all of these teams will get prizes. So if you come up and talk to us at the end of our program after the second talk, you will be able to get a prize. So our first team with 7 points is Team Motz. Where's Team Motz? Good job. You have good taste in cheese as well. The second one is Team Tiramisu, which is very cute. And these are our astronomy undergrads, and I don't know if they count either. Team 3 is Team Capstronauts. Good work. I, of course, approve of this, wearing a Capstronauts shirt. Our next team has a blank team name on it. Oh no. If you don't write a team name, it means you might not be able to get a prize. But I believe it was you, because you usually do well. I believe you. Make sure to write a team name next time. We have Team Amaze, Amaze, Amaze. Very good reference to Project Hail Mary, which I recommend to everyone read, or if you're not a reader, watch. The movie is quite good. Or both. And finally, Team Grace, which may also be a Project Hail Mary reference. So if you are one of the winning teams, please come up afterwards to get your prize. And if you are not one of the winning teams, you should study for next time. Good work, everyone. We'll now go into a brief intermission while we switch over to our next speaker. Please go patronize this establishment, go get a drink, maybe some food, go to the bathroom, do whatever you need to do. We'll be back in like 5 to 10 minutes. See you soon. All right, welcome back to part 2 of Astronomy on Tap number 106. For our next talk, we'll be talking about Apollo 14, and it is my very great pleasure to introduce Professor Jim Davenport, who is a research professor at the University of Washington. He is the director of the DiRAC Institute, which is data-intensive research in astronomy and cosmology. He's the director of the University of Washington's Outreach Program, and he is the 10-time winner of the University of Washington's Best Glasses Award. Please give it up.
Hey, how's it going? How many of you have a bunch of moon joy still from Artemis? Yeah, yes. I'm trying to capture that. I'm trying to put that out into the world. I want that moon joy for all of us. So I'm going to tell you about an Apollo mission that I was not super familiar with, not the one that I knew a lot about. I love the one before it because it's a great movie, and you should go see that movie with Tom Hanks as Jim Lovell. It's fantastic. But this is not that mission. This, I think, is the weirdest Apollo mission of all the 6 that went to the moon and landed. This one's the weirdest. This one is the most human, the most bizarre, and has the most strange stories. So I'm going to share a few of those with you. And I hope, in the end, we can all walk away with a little bit more moon joy, but also a sense that, like, humans went to the moon. This is something that people do, not like mythical figures. And I think that was the learning journey that I went on learning about this mission, is that these aren't gods. These are not like really heroes. They're just people who had a very strange job. They're weird people. Let's talk about the weirdest person on this mission. There it is. Alan Shepard. It was in the trivia. Alan Shepard was one of the Mercury 7, one of the very first astronauts that NASA recruited after we were already losing the space race. So one of the so-called Mercury 7 astronauts. And in fact, he was the only one that ever walked on the moon, the only one that ever made it all the way to the moon. He was the first American in space. He missed being the first human in space by about 3 weeks. We got really close. He was ready to go. He was apparently quite vocal about it. He was known as the Icy Commander, and a theme that comes up in this reading and in this work is that he's not always a chill guy. He is a relatively intense guy. He was a World War II pilot. He was a test pilot. He was extremely driven. A really interesting guy. So his NASA journey really starts in 1961 when Freedom 7, that was what he named the capsule, launched into what we called the first American in space. Now, this is like, he didn't really go to space. He sort of had a layover in space. It was a 15-minute flight. Very, very short flight. He left out of Florida. He went up and then right back down and landed in the Caribbean. Like, he barely went a few hundred miles down into the ocean. But still, it was a major triumph. This mission was a huge success, right? He was instantly a national hero. But it took a long time to make, right? So we were already years into the making of the space race. We were already weeks behind the Russians. We had already lost the PR battle. And Al finally goes for his ride for 15 minutes up and down. The day he goes into space is a really long day. He wakes up at 1 in the morning. He eats the most ridiculous breakfast of steak wrapped in bacon, eggs, coffee, and orange juice, and goes to work in this very strange job that he has. And then he gets his spacesuit on. He plays, I think, a hand of cards with somebody, and then he climbs in the capsule for his 15-minute flight, right? This is a very short journey. And he sits there, and he waits, and he waits, and he waits for more than 4 hours with a stomach full of coffee and orange juice and steak and eggs. And after about 4 hours, he radios into the ground station when the radio finally works again and says, I have to go to the bathroom. And they say, no, Al, there's no bathroom on your spaceship. You're not wearing an astronaut diaper. You have to hold it. For us to get you out to go to the bathroom, we have to unbolt everything. We're already 3 weeks behind. We're already 4 hours into this countdown. And so Al goes, okay. And he wets his pants. And I love that. And my 6 and my 9-year-old love that. It's the best part of this whole story. The first American we send in space goes up just absolutely soaking wet. He was laying on his back in the capsule, so it all pooled just right into his lower back. And that's how he rode to space. That's how this triumphant moment happens. This is the perfect allegory for what the space race was. These are not heroes. These are not gods. These are just people going up in space. Now, because I have little kids, they love these stories. These are the ones, they don't care about the rockets. They don't care about the moon. These are the stories they like. And there's so many stories like this. There are so many stories like, for example, on Gemini, a dual mission called Gemini 6-7, which that also really amuses them. Gemini 6-7, on Gemini 7, and that's Gemini 7 there, it's a 2-week mission. On day 2 or 3, a urine collection bag tears, and they're stuck in their capsule in essentially a flying outhouse for 2 weeks. They also, one of them forgot a toothbrush. And it just poses so many questions. What do you do for 2 weeks when you're basically sitting in the front seat of a car with somebody with one toothbrush? I'll let you ponder with your seatmates what choices you would make for 2 weeks. Another good example is up on Apollo 10. They flew around the backside of the moon. It's an incredibly inspiring story. There was my kids love this part. There was a little poop floating through the capsule, and nobody would admit whose it was. And it's written down in the logs. You can go find this in the radio logs. They're debating about whose it was. No one will own up to it. I love it. So Al makes it back successfully. He gets picked up by an aircraft carrier. Freedom 7 is loaded aboard. He is a hero. Ticker tape parade. It's fantastic. Presumably he takes a quick shower. Within about a year and a half, he's grounded from flight. And it's found out that he's been having dizzy spells. He's been having vertigo. He's been having a lot of problems with his inner ear. He probably was having it before Mercury 3. And he's grounded for this condition called Meniere's disease. I'm not that kind of doctor. Forgive me if I'm pronouncing that wrong. He's grounded. And at the time, there's no cure for this. There's nothing they can do about it. Al, again, famously has no chill. This is not somebody who likes to ride a desk. He wants to be in a cockpit. He does not give up on this. He goes into being one of the heads of the astronaut office, helping other astronauts. He's supposed to go on one of the Gemini flights. Somebody else has to go up there in his stead. He has to send his friends up there to do the thing that he wants to do, and it eats at him. It eats at him for years, for like 7 years. And this is where the story turns into more of like a soap opera to me. In 1968, as we're through the Gemini period and into the Apollo period, we're getting ready for those last Apollo missions that are going to go to the moon and actually land. Al checks himself in secret into a hotel in Los Angeles. Another astronaut had told him about a doctor that he had met that was an expert in inner ear conditions and basically had a new procedure to put tubes in your ears that could help drain this fluid and help regulate your balance. And Al said, I'll try anything. And against the advice of the flight surgeon and with no knowledge of his boss, he heads to LA. I don't know, I will admit, I put the mustache on him. I don't know that he wore that exact outfit. He went under a secret name, Victor Poulos, and he got an experimental surgery in secret. And a few days later, he was back in Houston saying, I'm all better. That ear thing, it's gone. I'm ready to fly. And the flight surgeon and the head of the astronaut office, who was one of his friends, said, it sounds like you are. And they put him through rigorous testing, really, truly rigorous testing. They made him fly up and down in the Vomit Comet. They made him do a bunch of high G tests in a bunch of test planes. They really put him through the ringer, and it seemed like he was better. What's also interesting to me is during this interim period where he's kind of sitting behind a desk, getting angrier and angrier, he also becomes a millionaire in the 60s through like real estate and banking investments, which I think is really funny. And I'm sure it had everything to do with his charisma and genius and not the fact that he was the most famous human being in the whole wide world. And like, why would you not buy a house from him, right? Like he could sell anything. But I think it's interesting. His biography really celebrates that he was the first millionaire astronaut. I'll let you decide if that's a good outcome or not. So Al gets himself flight ready. He's done the testing. He's made a bunch of money. He's bought very dapper suits. He's been on the Tonight Show. He pushes his way back into the flight rotation. And I mean literally pushes his way back in. There are people ready to go. Apollo 10 is flown. And the tradition at this point is when you fly on a mission, you are next 3 missions later. And he breaks his way in. And that's because his buddy here, Deke Slayton, And I love this at this time. All the astronauts have names like you'd give a dog. Deke and Al and Wally. Deke Slayton is now the head of the astronaut program. And he helps Al get back into the flight rotation and assigns him a seat, assigns him in command of Apollo 13. And Al says, this is fantastic. I'm not superstitious. This is great. I'll take Apollo 13. And it's the only time in this era that the NASA administrators say, no, thank you. And they say, you can't have Apollo 13. And they don't ground him, but they say, you're not ready. Nobody knows if you can still fly. You haven't flown in like 8 years. You're not ready. It gets escalated to the White House. And Richard Nixon, apparently, evidently, said, that doesn't make any sense. Al Shepard hasn't flown in like a decade. I thought he was just like a golf star at this point. Why would we give him a spaceship? And so he has to wait for 14, and he's not that happy about it. And now, if you know anything about the story of Apollo 13, this is the mission where NASA discovers that superstition and bad luck is actually real, right? This is the mission where we discovered that like 13 is truly an unlucky number. And the brave astronauts and the thousands of people down on the ground fight and struggle to get these people home. And the outcome is that the Apollo 13 mission, as the trivia suggested, is not complete, right? We don't actually go to the Frau-Morrow Highlands. We don't actually collect the rocks that the scientists want. And so NASA says, you have to go do Apollo 13's mission after they've already been training for 14. Al is super happy about this. He's not happy about it. But he'll take any ride to space that he can get. And so here he is with his hand-picked crew. We've got Stu Roosa, Edgar Mitchell, and Al Shepard. They all went by these little like 2-letter, 3-letter names, Stu, Ed, and Al. And here, this is the crew that he handpicked to fly on perhaps the most important, well, after Apollo 11, the most important mission that NASA had flown. At this point, Congress is already cutting funding. They've cut back from 20 Apollo missions to 17. They're already cutting missions. And there's a threat. Look, you just totally boffed Apollo 13. If you have another mission failure, this program is done. So there's a ton of pressure for these guys to get this right. They need to bring these rocks back. They need to carry this mission out perfectly. It's really interesting then that Al Shepard picks 2 rookies. These guys have never been to space. They're good pilots. Stu was a forest fire, fire smoke jumper, and Ed is an engineer and a pilot. They're good astronauts, but they're untested. And Al has spent, remember, a total of 15 minutes barely in space. Not necessarily your go-to guy, but everybody sees him as the ice commander, as the tough guy that won't give up. And so they decide this is how they're going to do it. Now, they give Al all kinds of grief for being old. Remember, he hasn't flown in 8 years. He is insanely old at the age of 47. He is much older. He's almost 10 years older than the other 2 astronauts on board. And I point this out because if we think back to something that happened just a few weeks ago, this wonderful mission, Artemis II, Al Shepard would be tied with Christina Koch as the youngest astronaut on that mission. She's 47. Everybody else is in their 50s. It's interesting. Anyways, they give him so much grief about this. Even when he's on the moon, he's like, not bad for an old guy. And so in January, around 4 o'clock in the afternoon, on a pillar of light and fire, Apollo 14 goes up. It really is an amazing piece of footage. I can watch these clips all day. They really are amazing. It launches. The launch goes fairly well. There's only a couple of small delays in the countdown. Al Shepard finally properly goes to space. And everything goes well for the first day or so until the first major milestone, after they've pushed off towards lunar orbit. Now, one thing you have to know about the Apollo missions is they bring everything with them that they need. They bring the rockets. They bring the capsule that the astronauts are sitting in. They bring the service module, which has like the rocket fuel and the oxygen and the electricity, and they bring the lander. Everything you need to get to the moon, land on the moon, get off the moon, and get home, right? But like IKEA, it's much easier if they ship it to you in pieces and you build it when you get there. And that's what has to happen with Apollo. You'll notice that when it launches, because of geometry, the pilots are all up here, and the lunar lander is down here, and there's no way for them to crawl through all this hardware to get to this. And so the first major milestone is they have to undock and flip around, as this great retro art illustrates. They have to flip the command module around, and they have to dock with the LEM, the lunar module, and pull it out. Now, this has been tested since Apollo 8. It worked in Apollo 10 very well. Obviously, 11 landed, 12 landed, third time's the charm. This should be fine. Stu Rosa has a sense of pride. It's his first time in space. He wants to make his name known. His goal, he says, is to be the fastest. I'm going to do this with the least amount of fuel. I'm going to get it on my first go. And he lines up the command module and puts it straight in the middle, right where it needs to be, and it doesn't latch. And he doesn't know why. So he backs up and does it again. And like me parking in an IKEA parking lot, he backs up and tries it again and tries it again. 6 times for 2 hours. He tries to park this thing. He keeps getting it dead on, right where it needs to be, and it will not latch. And he does not know why. And the engineers finally say, look, you're on target, and we can see that you're scratching the latches. We can, like in the camera, we can see that you're banging up the clips. You're clearly where you need to be. Why don't we just tell the computer that you did latch and see if that makes it go? So basically, they just turned it off and turned it on again, and it worked. They still, to this day, don't know why it didn't latch. But they said, yeah, it's probably fine. I mean, you only have to do that one more time when you come back from the moon. It'll probably be fine. And so off to the moon they go. This would have been the end of the mission. This would have been a disaster, right? This would have been the end of Apollo. Poor Stu. But they fly then 240 some odd thousand miles, pretty much uneventfully to the moon. This part goes fantastic. They're doing TV broadcasts, and because it's the 3rd mission to land on the moon, like nobody's watching. Like America's already kind of gotten over it. It's one of the lowest watched lunar broadcasts in the whole mission, in the whole series of missions. I like this little diagram of all the landing sites. Every one of these sites is still an area that we interact with as astronomers. We shine laser beams at the moon regularly, and well, not me, but other astronomers shine big laser beams, just like this. Shine laser beams at the moon. They bounce the laser light off of the mirrors that are left there, and we receive a few photons of light back. We can use that to measure through the speed of light the distance to the moon. So these are still active research laboratories in this way, and it's nice that they're sort of spread out over the surface. There's actually a couple of Russian stations as well that we can do this with. It's really neat. Here's Apollo 14's landing site in the Frau Moro Highlands. It's a piece of land that is ancient. It's the original lunar surface covered in big boulders from an impact. So the idea was you want to go to this rocky spot with lots of original terrain that is covered in the rocks that were thrown from an impact, that were chucked up. So you get both the stuff that was down deep and the stuff that's on top. The idea was that it's a really diverse area, perhaps one of the most important areas geologically in all the Apollo missions. So about 5 days into the mission, they separate. They leave poor Stu sitting by himself with his thoughts and a camera, and they head down to the surface. Edgar Mitchell piloting the LEM, and Al Shepard giving directions the entire way to a place he's never been. Upon descent, the radar goes out. They decide not to abort. They were going to do it anyways. They decided they would go whether they had radar or not. At one point, the spacecraft is throwing abort signals, and NASA decides that's because there's a switch where a loose wire has lost contact. And I swear to you, the advice is, hey guys, try hitting it. And the advice is, just hit the dash and see if that doesn't clear the abort signal. And it does, until it doesn't. And then 5 guys from MIT rewrite the LEM's control software in real time and send them instructions on how to patch this in real time while they're descending. It's pretty amazing. In a couple hours, they fix this computer. They override the faulty abort switch, and they land safely. What's amazing to me is this landing is the most precise landing of all the moon landings. They land within 200 feet of the target. So close. 250,000 miles, and they land within 200 feet. Here's Edgar Mitchell deciding to jump the last 3 steps on his way down to become the 6th human being to walk on the moon. Al, not a great cameraman. They took almost the fewest number of photos of any lunar mission. They were not great artists. They spent 33 hours on the lunar surface, exploring in 2 EVAs, extravehicular excursions, activities, moonwalks, we would say. One was short in distance, but was 4 hours long. And then another one was quite long in distance and was about 4.5 hours long. They did, as the trivia suggested, put a bunch of experiments down, including these mirrors that we still use to bounce little pretty green lasers at. Again, they're not great cameramen. You have to, this is their footage, not mine. I really like these visualizations that we have now. We have Google Earth, essentially, for the moon, right? We have the moon mapped in high resolution, and we can chart out where these excursions were. Here is where the flag and the lunar module, the landing module is. Antares is the module. And here is the second EVA, the second walk, more than 1 kilometer away, uphill. This was an incredible walk. This took them almost 3 hours to get to the end of this walk until NASA said, you have to turn around. These guys were getting exhausted. They're carrying equipment. They're collecting rocks. They're dragging equipment through a hill, a sandy, loose, gravelly hill. They're sort of slowly trudging up, trying to get to this site called Cone Crater. This was another one of those big impact regions they wanted to collect samples from. They wanted to see what the edge of the crater looked like, how soft was the material there, how well mixed was it. They have a bunch of great names. This was Weird Rock on the way back. This was Weird. I don't know weird what, just weird. They thought that was weird. And then they walked all the way back. This is amazing. And there's a couple of photos. I don't have one right here. There's a couple of grainy photos they took when they were out here looking back at the lunar module. When you're on the moon, you have no sense of scale, right? Everything looks truly alien, truly unusual. You don't know how big the rocks are. So they kept thinking like, God, we must be miles and miles away. Look how small that rock is. And then, oh, actually, it's just a small rock. Right? They had a really hard time judging distance. And they didn't know how close they were. The goal, the big science goal, was to drop some equipment and to collect rocks right here. And they couldn't get there because they were exhausted. They managed to make it within 100 feet of the Cone Crater, and they had to turn around. This irritated the geologists, and it made Al mad because he doesn't like to take the L. He doesn't like to be defeated. So Al says, if I can't make it to the crater, I'm going to do the next best thing. I'm going to get the biggest rock that I can, and I'm going to take that home. Apollo 14 brought home about 20 pounds more lunar rocks than Apollo 12, so they beat that. And they brought back the biggest rock until 15 beat them, and then 16 beat them, and 17 beat them. So they now have the third biggest rock. And they called it lovingly Big Bertha. What a charming name. It was found right by the edge of Cone Crater. This is the actual original photo. So this is Bertha covered in the dust of the lunar surface. And then here it is sitting in the lab. It's been heavily analyzed. It's a large rock, 20-pound rock. This is a properly big rock for you to carry. I don't know that I could carry right now a 20-pound rock uphill for a mile and not really question my life. And they did it in a spacesuit. Now, they didn't carry it in their arms. That would be crazy. Okay. Yeah. One of the great things is a recent paper suggested that this rock has the chemical composition of an Earth rock, not a moon rock, which is hilarious. Because if true, it's a rock that was impacted from Earth and thrown to the moon, and then we brought it back. Now, this is not universally agreed on, but I think it is hilarious. There are other papers that strongly disagree with it. Basically, they are arguing about chemistry that I don't understand because I'm not the kind of scientist. But I think it is hilarious that there's a possibility that Al Shepard brought back the oldest Earth rock. Now, you can't carry a 20-pound rock for a few kilometers on the moon by hand. That's just silly. And that's not what they did. They stuck it in the modular equipment transporter, which we would call a space wheelbarrow. Or I don't think it really looks like a wheelbarrow. I think it looks kind of like a stroller. Or if you look at it, if you look at the design, it has one handle. Yeah, it's got the two tires. It has one handle here. And you're meant to just drag it, like through the dirt, like a wagon, like a little kid dragging a little red wagon to play and to collect rocks. This is literally what my children do. I think it's super charming. Here you can see Al. You can tell it's him because he has the stripe on his helmet. Here he's got a camera, which he doesn't know how to use. Here he's got like a shovel. Here's some equipment bags. I think this is where Big Bertha went. And then they drug this thing through the dirt, through the lunar soil. It has BF Goodrich, I think, or maybe it's Goodyear tires. I forget who made the tires on this one. They are the only rubber tires on the moon. They are full of a very small amount of air, mostly nitrogen. There was a lot of design challenges getting just the right pressure so they didn't completely explode when they hit the surface. The idea was like a buggy or like a stroller, you want nice big wide tires so you can roll over the rocks. And yet they didn't appreciate just how sandy and loose the material on the moon is. And apparently this was an absolute nightmare. This was the worst thing to drag for kilometers across the moon. And this is why in every other mission after that, they brought a car. Much, much, much better. And they went way further as a result. Really, really cool. So this is the only time, again, it's a weird mission. It's the only time that we used the modular equipment transporter. Apollo 13 had one. They had planned to use it. But it got tossed into the drain. They didn't end up using it. Now, also, if you paid attention to the trivia, Al Shepard decides to do one other very iconic thing during this mission. So the astronauts, they always bring personal effects with them. They always try to bring something. Usually it's very poetic. One of them on Apollo, I think 10, brought the Bible and read verses when they first saw the Earth, right? It's very poetic, it's very beautiful. Al smuggled in his pocket, in one of his cargo pockets on his spacesuit, smuggled the head of a 6-iron golf club that he had welded and modified to snap onto one of the collapsible shovels. So this part is the actual equipment shovel that he's supposed to be using to collect dirt and samples with, and instead he rips the head off that and puts a 6-iron. I think a Wilson 6-iron. And he decides the last thing he's going to do while on the moon is hit 2 golf balls that he also brought in his other pocket. And you can see him in this clip. This is the best quality clip I can find. It's pretty grainy, but you can see him like, let's see if we started here. You can see him kind of pull out the golf balls, drop it on the ground. Now again, they had a one-handed cart. They couldn't even do 2 hands on a wheelbarrow, right? He has to hit this golf club one-handed. He doesn't plan this out especially well. He's standing awkwardly on a hill right next to the lander. They're exhausted. They've been outside for almost 5 hours. And so he just smacks this ball one-handed, and he just totally eats it. And in the audio, you can hear him say, "Oh, I shanked it." And he just gets a whole big divot full of moon dust that he just flings out. So he takes a couple more swings at that ball, drops another ball, and actually connects with it. And he says, "Oh, look at that. It's going for miles and miles and miles." That's what he says. This is poetic. It ends up going about 150 feet. But that's pretty good. One-handed golf shot in a suit, 250,000 miles from home. Pretty good. This is the most iconic moment of this mission. Somebody told me when I was researching this that, oh, Apollo 14, this is the most arrogant mission of all the Apollo missions. And it is. This is ridiculous. Why would you waste your moment after 10 years of working on it to hit a golf ball? It's ridiculous. The geologists were furious. Some of them wrote like angry letters to him. But this is also the most human moment, right? I don't know. I don't like golf. It's not my thing. But I would probably bring some kind of nerdy video game stuff with me, or a little lightsaber or something, right? Wouldn't you bring a cool trinket that meant something to you? And golf meant something to Al. He was a lifelong golf fiend. And he ended up donating this club back to the U.S. Golf Association, and the Smithsonian got a replica. He cared a lot about this. This is a very human thing to do. And it was the very last thing they did. The next thing they did was they took their backpacks and their tanks off that they were carrying on the moon, they chucked them on the ground, and they left. Oh yeah, here's the shot that proves that the photo that proves it didn't go that far. It's okay. It's okay. Somebody else is welcome to go up there and beat his record. Here's one of the backpacks they chucked after that, and they left. This is one of the last photos they took on the moon. So then, after 33 hours, they leave their campsite, an absolute mess. They take off, leaving Frowmore Highlands behind. I like this grainy 16-millimeter clip because as they sort of pitch around here, you can very faintly see these lines here. Some of these lines are the tracks from the wheelbarrow, the wagon that they're dragging. You can see it. You can see a couple of the instruments, the little shiny things, a couple of the instruments they left behind. This is very cool. And off they went. Now, we've talked a lot about Al Shepard here. We've talked a lot about his peculiarities. The astronauts as a whole, they bring strange stuff into space all the time, it's worth noting. John Young, which was not one of the trivia answers, but was one of the false answers, he and, John Young and Gus Grissom got in trouble on Gemini 3 for bringing a corned beef sandwich up to space. for a 4-hour mission. Like, he could not wait 4 hours for a corned beef sandwich. And then Wally Schirra, who apparently put him up to it and got him the sandwich, a few missions later on Gemini 6, brought up a harmonica, which is very cool, the first musical instrument ever in space to be played, and also brought up scotch and cigarettes. He was a, quote, known prankster, Wally Schirra. There are a lot of other peculiar things. Both the astronauts on this mission other astronauts brought up peculiar things. Let's talk about a few of them. And for one of them, I want to try an experiment. We're going to recreate one of the experiments that one of the astronauts did from basically one of their personal effects. So this is an experiment to me. We'll see if this works. So I brought here one of my kids' decks of cards. What is your name, sir? Would you be willing to help me with my experiment? Thank you, Jason. Jason, would you? Yeah, I'm not a magician, so this is going to go great for both of us. Would you please cut this deck of cards? Yeah, like in the middle. Fine, good, okay. Close enough, fine. Okay. So, Edgar Mitchell, this is the lunar module pilot. Edgar Mitchell is a lifelong aficionado, I should say, in spirituality and in mysticism and collective human consciousness. And he's convinced before Apollo that there are experiments proving that ESP and telepathy is real. I am not here to convince you of that one way or another, though we will perhaps convince you in just a moment whether or not this is real through our experiment with me and Jason. During his downtime on the way back from the moon, he conducts private experiments during his free time. They're just sitting there. They're just waiting. He has friends at home that he has given cards to. And then in space, he's trying to test, can I read the cards? And then he writes down his guess. Then a week later, he checks the answer. He's trying to determine, right, is he closer to the spiritual nexus that binds all of humanity or something? I don't know, the force or something. I don't understand this myself. Let's find out. I am not an astronaut. I am an astronomer. Very close, very close. Let's find out. Okay, Jason, can you pick that card up? Don't show it to me. You know how this works. Okay, show it to somebody else. Keep it honest here. Okay, I'm going to use my astronomer powers, which are very similar to astronaut powers, to try to divine what that card is. Is it a King of Hearts? No, tell me the truth. No. Okay. I am not an astronaut. Unfortunately for Ed, he also only got like 30% of these right. He argued that that was good evidence. He argued that that was actually something we should believe in. But, you know, I don't know. We need to talk about the statistics here. But I will say, most of the people at NASA actually didn't have a huge problem with this. Wernher von Braun, who was like the Nazi fleeing godfather of the space race, a complicated and interesting figure, came to him and said, I actually thought this was kind of cool, and suggested that he find other ways to experiment with this in a more controlled laboratory setting. I think that's pretty neat. The last thing that I wanted to talk about, we already talked about it in trivia a little bit, and that's Stu Rosen. So he has a lot of time to sit here and think in orbit by himself about how he messed up the docking. He does a good job on the return flight home. Everything goes well. Stu was an old forester and a smoke jumper before he was an astronaut. A really brave and interesting guy. And he brought with him, upon suggestion of some foresters, a can of seeds, about 500 seeds of different types of trees. And they were planted around the world in what became known as the moon trees. Now, this was a little bit of science, like a lot of things in the Apollo mission. It's a little bit of science. Will the trees grow? Maybe. They did. They did. That's one of them. What I think is really cool is they were planted everywhere. And this is more than 50 years ago now. The trees that survive are really mature. We actually have one in Olympia, a big Douglas fir down by the Capitol. It's on the Capitol grounds. I've never seen it. I learned about this just yesterday. I think this is so cool. To me, this is really the legacy, right? Human beings, weird, flawed, greedy, impatient, grumpy, icy human beings, did a really beautiful thing, right? They went to a really amazing place on behalf of everybody, and they brought back the literal and figurative seeds that inspire a lot of things. And about 9 days into the mission, they land. This is the Kitty Hawk command module on display now in Florida, almost right where the mission started. They landed safe and sound, pretty close to the Cook Islands in the Pacific. This is a good moment to end, the end of the mission. And so I will leave you, we will wrap our story up of what I think is the most unusual, most peculiar, most space opera-y of all the Apollo missions, Apollo 14. I think this is a fitting photo. Here in Frau Mora, in the highlands, where Apollo 13 tried to go, sitting slightly on a hill, with the shadow of Al Shepard still on the moon in some way. As a little kid, I see this, and I think these are heroes. These are the people that I aspire to. And then as an adult, I realize, right, they're not paragons of virtue. They are just people. Weird, flawed, very driven, strange people doing an amazing thing. And I think I'm still filled with wonder. I think I still want to go here, if I could. I think a little bit of wonder is how we should finish this talk. Oh, Jason, is that your card? Okay. It is. Thanks, everybody. Thanks, man. They're not all sixes. There you go. Yeah. Right here?
Yeah, right there.
Yeah, they would have been on more than a hill if they had missed the target. Yeah, I mean, this was a problem. As they're coming down, so one of the questions is, what if we missed this moment and we hit this divot here? The LEM has slightly adjustable feet, so it can tolerate this to a degree, but they are on a hill, and this becomes a little bit of an issue because when they launch, they're launching on a slight angle. As they're landing, they're like literally looking out the window, trying to figure out where to touch down. At like 50 to 100 feet above the ground, the rocket is just pushing, and they are trying to figure out where to turn it off to fall the last 50 feet or so to just slam down on the surface. It is not the most gentle surface touchdown, but this one was very precise. It's a big problem. It's a big concern. It's a good question. Yeah. Yeah, the question is, how do we navigate on the moon? So the geologists really tried to prepare them. They had all this aerial photography that the other astronauts had taken. And so what Stu Ross is doing for 33 hours is taking photos of the next landing sites, trying to get different angles and different illuminations because the sun's in a different place. You're trying to figure out how high these little valleys and divots and mountains are. Some of these areas are really hilly. Then you land on the surface and nothing looks familiar. Even though you go to Arizona and you go to Hawaii and all these places with different topologies, nothing looks sensible. There's no trees, there's no stops, there's nothing for your human brain to capture and say like, oh, I understand how big that tank is. I understand how big this table is, right? You have a sense of scale here. You don't have that on the moon. And this was a big problem for them. They knew which way to go. They had a compass, they had the stars, they had the sun and the earth. But they didn't have any sense for how hilly and rolly the terrain would be. And this, they thought, oh, this is the edge of the cliff, and then they go back down. And then they think, oh, well, it must be here, and they go back down. And because you're dragging this cart, and you're not walking, you're doing this, right? You're like hopping with this cart. It's hard work, and you really lose yourself. And you can see on the way out, it's a windy path. It's very hard. They found that it was very difficult, even with the maps and the simulated photos they had, the illustrations they had. They were kind of useless. Yeah. Say again. Yeah. Oh, yeah. The question is, how does the car work on the surface? It's an electric car, very ahead of its time. Gas wouldn't work on the surface. It's a small little, they call it the moon buggy. It's a small little, well, car is a kind of generous term. It's like a golf cart, really. It has a really low horsepower motor. But it does have, I think, four-wheel drive. I'll have to look this up. The tires on the space wagon here were filled with air and were rubber. And they decided this would not work scaled up to a car. It needed to carry a lot of weight. It needed to carry 2 astronauts and more Big Bertha type rocks. And so they couldn't carry that just with rubber tires. So they switched to a tire made out of piano wire. And they made a tire that's mesh. This is metal mesh tire. It's not air-filled. And so it sat there sort of like smashed up, folded up. And the first thing they did was it was folded up. I don't remember which of the legs of the LEM, but the car was kind of folded up in the legs on a harness. The first thing they did is kind of like winch it down and let it down on the surface and then pop the wheels out and turn it on and make sure the battery still works. And then they drove it around. It was very cool. Okay, last question.
Compass work on the moon? You mentioned that a second ago.
I think a compass works in the moon, but not well, and not in the directions that we would think. I don't know where the magnetic North Pole is in the moon. So it's a good question. I don't know. I may have misspoken. It's a good point. Okay, thanks everybody.
All right. Thank you everyone so much for coming. As a couple brief reminders, while I'm getting my computer back plugged in, let's give another round of applause to our great speakers. All right. I promised Hurum that I would put the eSteam QR code back on the screen, so if you're interested in helping out, you can. All right. So here is again the eSteam QR code if you're interested in helping tutor incarcerated youth, or you're interested in giving to the cause. And if that QR code is too big to scan, let me know and I can give you the link later. Our next Astronomy on Tap is on May 20th at 7 p.m. right here. I hope to see you all there. And if you won trivia, as a reminder, please come up and get a prize with my lovely assistant Barbara. And with that, thank you all so much for coming. Have a nice night and get home safely.